Hi guys, today's topic is thermal design of heat exchangers. So I'll be giving different videos for the different topics. The first one will be introduction. Today's lecture will be an introduction. So I'll be covering the oncoming videos and with a small description. Then I'll be also giving the contents of the future videos. To start with, so I'll be just using J factor and F factor invariably in all of my lectures. This audience I am focusing will be the practicing engineers in the design field in heat exchangers and the students in the research areas, graduate and undergraduate level, and these people will be benefited by this lecture, I believe. So I'll be dealing with all kinds of heat exchangers. To start with, I'll be going with the air-cooled heat exchangers only. So this lecture will be covering air-cooled heat exchangers. So in this, I'm just going to talk about the J factor, F factor, how we are going to obtain these values for different heat exchangers configurations. So we'll be basically dealing with tube and fin configurations and the bar and plate or the plate fin type heat exchangers which are normally used in several applications. So J factor, F factor, I just want to give a briefing about that. J factor deals with the heat transfer and F factor represents the pressure drop of the heat exchanger. So why we are talking about these factors? Because we are always dealing with non-dimensional numbers in heat exchanger design. So like Reynolds number, you might have heard of Reynolds number, Prandtl number, Nusselt number, and then Stanton number, and J factor, F factor, etc. So many numbers. So it is very convenient for us to talk about these numbers when we are using some equations or when we are deriving something or when we are designing these heat exchangers. Instead of talking in a lengthy fashion and then remembering all those equations, so we will just cut short. We will just go for J factor and F factor, and then we will have a chart or a graph, so which will represent for different Reynolds number, air-cooled Reynolds heat exchanger, Reynolds number versus the J factor, Reynolds number versus the F factor will be found in literature. And then we can also get this J factor, F factor by using wind tunnel testing with good instrumentation. So in this, actually there are different types of methods available with steam boiler and without steam boiler. Wind tunnel can be used without steam boiler and with steam boiler. On the hot side, if you are using steam, then what will happen is it will be a very easy procedure to get the heat transfer coefficient on the air side. Suppose you want to develop a fin, newly developed a fin, you want to find out the factors like J factor, F factor. So normally we will be going for a wind tunnel testing with the air-cooled side. We will have the unknown fin for which the factors are required. The known side or the hot side will be using the oil or water glycol mixture like that. So what are the advantages of different methods? See, if you use steam on water side or oil side, hot side, so it is very easy for us. It is something like eating a banana. So this procedure, if you go for the overall heat transfer quotient, then in that we can find out the overall heat transfer quotient is a mixture of the air side heat transfer quotient and the water side heat transfer quotient, the fouling factor, and the wall conductance. Wall conductivity will be minimum. We are ignoring in this our lectures. We will not be considering. But in very big heat exchangers, so normally there will be conduction. So like the conduction will be a phenomenal item. So we cannot ignore that. But for our purpose, in normally what we are using, these are all medium-sized heat exchangers. So the length and the width will be, actually will not be giving very much variations in the conductance or conductivity or whatever. So we can ignore conduction in this calculation of overall heat transfer quotient. Why we are bothered about overall heat transfer quotient is, once we get this value, it is called U value. Overall heat transfer quotient is called U normally. So this will be representative of the water side and the air side heat transfer quotients. So once you find out this one, then you can always calculate the heat transfer by having some equations like Q equal to UA into delta T LM or something. You can use different methods. For example, the logarithmic mean temperature or epsilon and NTU method. Epsilon NTU method is dealing with number of transfer units and the effectiveness. It's basically an effectiveness based approach. So what is effectiveness and all that we will be talking later. So it is easier to follow NTU and epsilon method rather than log mean temperature, because the log mean temperature is an iterative process. Suppose you don't know the outlet temperature of a cooling medium, whatever the air exiting from the radiator, we don't know the temperature. So and then what we want on the hot side we know the delta T or whatever, on the oil side we know. Then what will happen is it is very difficult to assume some value and then fix the value for air side exit value. So what we do is we assume some value and checking the logarithmic mean temperature and go on iterating until it converges. So that's a very cumbersome procedure. So normally we are adopting number of transfer units and effectiveness method. That's the second procedure. So I'll be detailing in a different video. Now in this all the properties of air, oil and water and glycol water mixture, so this will be given in the reference textbooks. So I given the names of the books, data books. There are a number of data books available. So I am referring one C.P. Kodanraman and Subramanian is a HMT, that is heat and mass transfer data book. So I'll be using in my calculations and all kinds of software. And then this will be actually this is the textbook. Actually, this will be used for all kinds of heat exchangers, not only air cooled. So now we will be having the videos. I'll be just giving you the ideas about the different videos. So this is a video number 1. It is actually introduction to thermal design of air cooled heat exchangers. Video number 2, I'll be talking about reference books and technical papers, whatever is relevant to heat transfer design. And video number 3, I'll be talking about units which are used on heat exchangers thermal design. And video number 4 will be non-dimensional numbers. It will be focusing on Reynolds number, Prandtl number, Nusselt number, Stanton number, J factor, F factor, etc. Then video number 5, there will be a lot of compilation of J factor, F factor. So all the data available in literature, so I will be compiling and giving it to you. This will be covering individually finned tube. It will be covering also flat fin with array of tubes. It will be covering bar and plate or plate and fin heat exchangers also. And then for J factor, F factor will be used normally in two fashions. One is if you want to develop a new fin. I told you earlier, if you want to develop a new fin, you can use the new fin on the air side and the hot water or the hot steam on the hot side. If you use steam on the hot side, it is very easy to find out the air-cooled air side heat transfer coefficient. It's very easy. It's not cumbersome. Whereas if you are going for a hot side, water or water glycol mixture or oil, then it will be tedious. It's something like cutting a jackfruit. You have to separate all the data. So it's not so easy. It is time consuming. So normally if you have got a steam boiler and a wind tunnel and a tool room, dedicated tool room, you can develop your own fins and you can test it extensively, and then you can get your own J factor, F factor. So along the data available in the literature, you can also develop your own factors in future. I mean, whatever, if you want, you can develop and keep it in storage. So that will be used for your future applications. And then I will be just covering the topics on video number 8. So that will be actually fin efficiency estimate. So I will be giving the various fin efficiencies for various fin configurations. For example, bar and plate, you can have OSF fin, offset strip fin. So what is the fin efficiency? And then McCord fin, what is the fin efficiency? And then different configurations, tube and fin, what is the fin efficiency, how to calculate. And then video number 9, so I will be focusing on hydraulic diameter. Hydraulic diameter is very essential in calculating Reynolds number. So normally I will be just briefing you about hydraulic diameter in video number 9. Video number 10 will be talking about different aspects, so which will be useful for arriving at the overall heat transfer quotient. One is the free flow area of the core, then the core mass velocity, and the core frontal area, and core Reynolds, the Reynolds number in uh, the heat transfer design. Then video number 11, I will be focusing on, suppose you got a tube and fin configuration. A customer is giving a tube and fin configuration. He does not know values of heat transfer and the pressure drop. He is just giving a sample to you. Then how to convert it to your own configuration. Suppose you are developing bar and plate radiators only. So then what will happen is, so you have to get the tube and fin sample, put it on your own wind tunnel, and then check up all the values. You get your own heat load and pressure drop, and then same thing can be, you design your own bar and plate to suit the heat transfer and the pressure drop. Okay, if the pressure drop and heat transfer is given by the customer, then it is a direct calculation, or you can use your own software for getting the bar and plate configuration. Now, so I will be focusing on video number 12. I will be focusing on overall thermal quotient. So this is a very important step in our, it is a stage. Okay, there we are actually ignoring the conduction, wall conduction. So I'll be, the video number 13 will be focusing on cross flow and counter flow methods. Cross flow and counter flow, and the various methods to tackle these radiators using this flow. The one is the NTU method, then second one will be log mean temperature method. Video number 14, I'll be just giving you the references where you can get the data regarding the properties of air, properties of water, properties of oil, and properties of glycol water mixture. Video number 15, we'll have surface area for various configurations. Surface area, how to calculate. For example, offset strip fin, OSF fin will be very tedious. And then McCord, lower McCord fin, that also you have to calculate in some aspect. Tube and fin configuration, what is the surface area? Surface area, what I mean is the hot side and the cold side. It can be tube surface area, inner and outer, and the fin surface area on both sides. And then similarly, all other configurations I will be talking later. So these are the 15 number of videos I will be covering shortly in future. Then usually we will be going for some kind of calculations, and then we can convert them into software. For example, if you are actually having a wind tunnel experiment, and then the data is you are getting, so you want to convert it to J factor, F factor, or vice versa. Once you have got a J factor, F factor, how to calculate the heat transfer and the pressure drop. So all these things, you have to have your own software. Usually you can write it in, initially you can write in Excel, and then you can use your Visual Basic. So it will be, you can have an easy accessibility by your team once you have Visual Basic. And Visual Basic is a user-friendly software. For any new development, or if you want to hop from one configuration to other configuration, it's very easy when you are using a software. It will not be time consuming, it will be easily done. So wind tunnel, you should have normally good instrumentation regarding air side, velocity, temperature measurements, and water glycol side, and temperature and velocity measurements. All these parameters have to be measured accurately, so that the overall heat transfer, the limits will be always met. So there is always a safety factor, so this will be met only with good instrumentation. And plus, we can also have your software to cross check. And normally in wind tunnel, we are going for a model testing. So this will not be actually the size, it will not be the actual size. We can have a model testing. You can always extrapolate, and from the wind tunnel data for whatever you get for the model, you can always extrapolate. So once you extrapolate, you will get the actual value required for the heat transfer and the pressure drop. So if this is the end of the lecture, and if you like this video, please subscribe, and then click the icon button, and then send your likes and comments to me. Thanks for watching, and thank you very much. Thank you.